dear students, Jai Hind. Myself Dr. Pankaj Goel, working as an assistant professor in Akgec Garg Engineering College. Today we will discuss a very important topic from the subject VLSI technology. The topic is packaging of VLSI devices. The content that we are going to discuss today is package functions, classification of packages, package types, packaging design considerations in VLSI, VLSI assembly technologies in VLSI, package fabrication technologies and references. So, first of all, let us discuss what are the main package functions for which the packaging is required. First, the mechanical connection of chip to the board is done with the help of packages. Second function, it removes the heat produced on the chip, that is as a heat sink. Third, packages are used to protect the chip from mechanical damage. As we know that VLSI chips, which are made up of semiconductor, they are very fine and consist of millions of transistors. So, it need to be protected from the mechanical damage, and for that the VLSI chip is encapsulated with the help of package. And another function, important function of package is electrical connection of the signals and power from chip to the board is done with the help of packages. Okay. Now, let us discuss the classification of packages. So, the classification of packages may be done on the basis of material used, on the basis of type of pins used, and on the basis of arrangement of pins. So, first of all, on the basis of material used, the packages may be broadly classified as plastic packages and ceramic packages. There are two broad categories, plastic packages and ceramic packages. Then on the basis of type of pin used, we have two types of packages which are named as through hole package and surface mount package. Through hole package is a earlier generation technology where the pins cross the board and they are soldered on the other side of the board. Whereas on the surface mount package technology, the pins are soldered on the same side of the surface where chip is mounted. Then the classification of package on the basis of arrangement of pins, the packages may be classified as dual inline package, single inline package, zigzag inline package, ball grid array and quad flat package. So, these are some of the commonly used packages on the basis of arrangement of pins. Some of the very popular package types are graphically shown here for the understanding. Here we can see we have a 84 pin PLCC, plastic leaded chip carrier package. Then we have this dual inline package. Then we have here, this is our quad flat package. So, similarly we have this our thin small outline package, and this is our ball grid array package, and this is our pin grid array. So, these are some of the very popular package types that are used in VLSI industry nowadays. Next important topic that we are going to discuss today is about packaging design considerations. Now, let us see the role of packaging. The packaging of VLSI devices plays a crucial role in ensuring the reliability, performance and manufacturability of the devices. The primary considerations in VLSI packaging design include the following: the thermal management, electrical performance, mechanical protection, interconnection density, size and weight constraints, cost efficiency, environmental considerations, compatibility and standardization, and in the last, reliability and testing. So, these are some of the important considerations that are to be taken care of while doing the packaging of VLSI devices, because these impact the performance, reliability and manufacturability of the devices. Now, we will discuss these considerations in a bit detailed manner. The first one is thermal management. We can see here, as the name suggests, the thermal means the heat dissipation is very critical to prevent the device from overheating, because overheating can degrade the performance and create reliability issues. Then thermal conductivity of the packaging material and the inclusion of heat sinks or thermal vias are essential aspects. So, this is about thermal management. Second is electrical performance. Now, the package should minimize the parasitic capacitance. As we know that parasitic capacitance is undesired capacitance which occur, and the package should be designed in such a way that the parasitic capacitance is minimum. The package should have minimum parasitic capacitance, inductance and resistance to maintain the signal integrity. Otherwise, if we have a large value of these parasitics, be it capacitance, inductance or resistance, it will compromise the signal integrity and the device may fail. So, for that, one thing that can be done is short interconnections that help reduce the delay and improve the performance. Next important design consideration is mechanical protection. As we know that our VLSI chips are very delicate, consist of millions of transistors on a very small die. So, to protect these dies or VLSI wafers from environmental damage, the package must be used. So, the package shield the silicon. The environmental damage may be in the form of moisture, dust and physical stress. So, to avoid such kind of damage, the material of the package should be robust and proper sealing techniques should be used. Next point is interconnection density. Now, the VLSI devices require a high density of interconnections between the chip and the external circuitry. As we know that VLSI stands for very large scale integration. So, there is a large integration of interconnections, and so the packages that we use must also support high integration, high density of integration. So, for that, advanced packaging techniques like flip chip bonding and multi chip modules are often used. Size and weight constraints. As devices become more compact, the packaging must also align with size and weight reduction goals. One of the important terminology that we use when we discuss VLSI is miniaturization. Miniaturization means we are reducing the size of transistors as per Moore's law. So, as the size of the transistor is reducing, so the size of the wafer or chip is reducing, and if the size of the chip is reducing, its weight is also reducing. So, the package that we are using to encapsulate that wafer must also obey those rules, that the size and weight of package must also be reduced, especially in portable electronics, because portable electronics they are preferred if they are lightweight and small size. Okay. For that, techniques such as wafer level packaging and chip scale packaging are adopted. Next is cost efficiency. Cost is very important. We always strive for low cost devices, because low cost devices can be the reach of low cost devices is to maximum population. So, the cost must be minimum. So, the package that we are using should be cost efficient. So, the packaging should balance the performance with cost effectiveness to remain competitive. Most production techniques and material selections are optimized for affordability, because affordability is very important to remain relevant in the highly competitive market. Environmental considerations, here we can see there are environmental standards such as RoHS. So, the packages that we are using must compliance with these environmental standards for material usage and waste management. And as some certain type of materials are to be avoided because they are harmful for the environment, such as lead. So, the use of lead free solder and recyclable material is emphasized. Next is compatibility and standardization. Packaging must align with the industry standards for compatibility with existing assembly and testing equipment. This ensures integration into broader systems without additional customization. So, we know that compatibility and standardization is very important for the interoperability of the devices. And the last point is reliability and testing. Packaging must ensure long-term reliability, including resistance to thermal cycling, mechanical stress, and electromigration. It should also facilitate efficient testing at various stages of production. So, the packaging should be such that it ensure the reliability and it facilitate efficient testing at various stages of production. Next topic is assembly technologies, VLSI assembly technologies. Now, in case of VLSI devices, assembly technologies play a vital role in integrating the silicon chip with its package, because it is not the case that we have covered our VLSI chip with a plastic package. They must be connected in certain ways, be it for heat sinking, be it for passing of electrical signal and power. So, they must be integrating the silicon chip with the package in a proper way. So, for that we are having assembly technologies to ensure the electrical connectivity, mechanical stability, and thermal management. The major assembly technologies include die preparation, die attachment, wire bonding, flip chip bonding, tape automated bonding, encapsulation, thermal management, surface mount technology, testing and burning. So, these are some important assembly technologies that need to be considered for die preparation. We must note that after the wafer is fabricated, the individual dies are separated using wafer dicing, typically performed with the help of a diamond saw or laser, and each die is inspected for defects before proceeding to assembly. So, that is the first step, die preparation. Second is die attachment. The die is attached to the package using some adhesive such as epoxy or eutectic bonding material. This step ensures mechanical support and heat dissipation. So, we are using some kind of adhesive material to attach the die with the package substrate. Next is wire bonding. For wire bonding, we are using either the gold, aluminum or copper wires. And wire bonding methods include thermosonic bonding, thermocompression bonding and ultrasonic bonding. These are the main bonding techniques. For flip chip bonding, here the chip is inverted and its solder bumps are directly connected to the package substrate. This method, this flip chip bonding method, offer higher interconnection density and better electrical performance compared to wire bonding. Next is tap automated bonding. Now, the chip is connected to a flexible polymer tape using fine metal leads, and this kind of bonding is suitable for high pin count devices and it offers lower parasitics. Then encapsulation. The assembly is encapsulated with protective materials, example epoxy resin, to shield the device from environmental factors like moisture and mechanical damage. Methods include transfer molding or globe top encapsulation. Thermal management. Now, for thermal management, we know that the heat sink, thermal grease or other heat dissipating elements are integrated into the assembly. SMT, the surface mount technology. So, as I told you, the through hole technology was the earlier generation technology. SMT is the advanced technology. So, for VLSI devices, they are often mounted on PCB using SMT techniques, which allow for compact and high density assembly. Then the next is testing and burning. Final assembly include electrical testing to ensure the functionality and burn-in test to identify the early life failures. So, conclusion here, these assembly technologies are critical in transforming a fabricated VLSI chip into a reliable and functional component for electronic systems. The choice of assembly method depends on the application, performance requirements and cost considerations. The last topic for today's presentation is package fabrication technologies. The fabrication of packages is a critical process that ensure the proper protection, interconnection and the thermal management of the silicon chip. The key package fabrication technologies are the substrate materials, lead frame fabrication, multi-layer substrate fabrication, metallization techniques, encapsulation, flip chip substrate fabrication, surface finish, thermal management features and package testing. Okay. In this, the first of all we will see the kind of materials that we can use for package fabrication. Here the materials that we can be used are of broadly two types, ceramic and organic substrate. For ceramic we may use materials like alumina or beryllia, whereas for organic we may use epoxy resin based laminates such as FR4. So these are the substrate materials. Then lead frame fabrications. Lead frames are used for electrical connections between the chip and the external circuit. And for this, the materials that we can use are silver or nickel to improve the solderability. Also, copper and alloys used for the fabrication of lead frame. Next is multi-layer substrate fabrication. Advanced packaging require multi-layer substrates for higher interconnection. We know that in case of VLSI, there are a lot of interconnection wires, and to keep the size in a limit, what we do, we use multi-layer technology, in which there are multiple layers on which interconnections layers are drawn, and these interconnection layers are separated by dielectric materials. So the layer of these conducting traces may be copper, and these layers, as I just told you, that they are separated by dielectric materials, or they are also known as insulating materials, and they are interconnected using vias. One conducting layer is separated from another conducting layer by a dielectric layer, but if one conducting layer is to be connected with another conducting layer, then a via is created between the two through a dielectric material. So for that, via is used. So fabrication step include photolithography, copper deposition and lamination of multiple layer under heat and pressure. Metallization techniques. Metal layers are added to provide the electrical pathways. Common techniques include sputtering, electroplating and CVD, chemical vapor deposition. And the most commonly used metals are gold, aluminium and copper. Encapsulation materials is epoxy molding compounds, short form EMC. They provide mechanical protection and environmental resistance. Then the flip chip substrate fabrication. Flip chip technology involve, as we also discussed previously in the assembly technologies, the flip chip technology involves direct bonding of the die to the package substrate using solder bumps. Surface finish. A surface finish such as solder mask or gold plating is applied to protect the exposed conducting areas, and it enhances the reliability. So for common finish include electroless nickel immersion gold and organic solderability preservative OSP. So these are the common finish materials that are used. Thermal management features include heat spreaders, heat sinks and thermal vias, and materials with high thermal conductivity such as copper and diamond composites are used. Package testing. For package testing, the techniques like X-ray inspection and the thermal cycling test are employed. These package fabrication technologies are continuously evolving to meet the demands of smaller, faster and more reliable VLSI devices. The reference books for this content was VLSI Technology by SMZ from McGraw-Hill Education, and second one is VLSI Fabrication Principles by Saurabh K. Gandhi from Wiley India Private Limited. So you may refer these books for detailed study. Thank you very much.